Welcome to this video on determining linear, quadratic, or exponential function based on multiple representations. By the end of this video, you should be able to identify whether a function is linear, quadratic, exponential, or neither from the equation, from the graph, and from a table of values. Let's take a look at our notes. First thing we're going to look at is from the equation. We've talked about this previously. When you're looking at the equation, it depends on the degree or the variable placement to determine whether we are linear, quadratic, or exponential. So in order for an equation to be linear, it's going to have a degree of 1, meaning the highest exponent is 1. So when we look here, this is really y equals 5x plus 1. That's 5x to the first. So the highest exponent is a 1, so that is linear. This is y equals 1/2 x. X is to the first, linear. 2x plus 3y, we're really looking at our x, just our x value here. X is to the first, so it is linear. In order to be quadratic, quadratic has a degree of 2, meaning the highest exponent is 2. So we see a similar setup. We have a y equals situation, but we have 2x squared plus 3x. Now, if we didn't have the 2x squared, this would be linear because the highest exponent would be 1. But you can see right here with an exponent of 2, the highest exponent is 2, making it quadratic. Same here. This is 2x squared plus 9. The highest exponent on our x is a 2. And then we have x squared plus 3y. Our highest exponent is 2, making it quadratic. Now, exponential. The exponential graph is going to have a variable in the exponent. So I always like to say the x is in the exponent for an exponential. So when you take a look, this is 3 to the x. The x is in the exponent spot. That makes it an exponential function. And that doesn't have to be the only thing up there. It could be 2 times x, or it could be x plus something or x minus something. As long as the x is in the variable, we're going to call it an exponential. So let's take a look at a couple of these. On number 1 here, we have 6 raised to the x. The x is in the exponent. That's going to make it exponential. Okay. Looking at number 2, y equals 7x squared plus 5x minus 2. The highest exponent is a 2. That's going to make it quadratic. 9x plus 3 equals y. The highest exponent is a 1 on that x, so that makes that linear. And 4 raised to the 2x equals 8. The x is in the exponent, making it exponential. All right, so that's when we're looking at our equations. Let's look at the graphs. The graphs are pretty quick and easy. If it's going to be linear, it's just a straight line. Quadratics, we just did these. They're a parabola. They can open up or they can open down for Algebra 1. Suppose the U-shaped curve is a parabola and it's a quadratic. And then for our exponential, it's going to rise or fall quickly in one direction. So this graph falls quickly in one direction, and you'll notice these columns line back up again here with exponential, quadratic, and linear. So if you forget, you can always follow the column up to remind yourself which one is which. So when we take a look at this graph, it's falling quickly to the right here. This is an exponential. This is a scatter plot actually, but if you could kind of envision the line and you can see it, that's also going to be exponential. This is a straight line, so this is linear. And our last one here, see how it's pointed on the bottom? That is not a quadratic. Remember, a quadratic is U-shaped, not V-shaped. So this is actually neither. It doesn't meet any of our criteria. This is actually an absolute value function, which is not one that we normally deal with in Algebra 1. All right, let's take a look on the other side. So the graphs are quick and easy. We're going to now look at a table of values. So determining linear, quadratic, or exponential, all x values must have some sort of common difference. So if it's linear, you'll never see the same y value twice. And something called the first differences are the same for the y values. Okay, so we're going to be looking at the y values of these graphs and looking at the difference of each number. So in linear, the difference is the same each time. In quadratic, you may see the same y value happen again, and the second differences are the same. So we'll take a look at what that means in just a minute. And with exponential, you're noticing that the y's change much quicker than the x values do. You never see the same y value twice. And you're going to have a common ratio, or that multiplication pattern like we talked about in sequences, for the y value. So here, let's take a look. So in this, we're just looking at our y values. To get from -2 to 1, you'd have to add 3. To get from 1 to 4, you would have to add 3. To get from 4 to 7, you would have to add 3. And 7 to 10, you're going to have to add 3. Notice that this has a common difference each time. This is what we call the first differences. If the first differences are the same, that's going to be linear. So this table represents a linear function. Okay. So let's compare that to what's going on here in number 10. So to get from -6 to -6, you would add 0. There's no difference between those two. To get from -6 to -4, you'd have to add 2. So we can see already this is not going to be linear. To get from -4 to 0, you would add 4. And to get from 0 to 6, you would add 6. So our first differences are not the same. So it's not linear. We know this. So now what we're going to do is we're going to look at these differences and check the difference of the differences is really what we're doing. 0 to 2, we're going to add 2. 2 to 4 is adding 2. And 4 to 6 is adding 2. Okay, we check the differences again. This is the second difference. Now notice in this that the second differences are all the same. The second differences are all the same in a quadratic. So this table of values represents a quadratic function. Okay, let's try it again. We'll move down here to 11. Now, when there's decimals like that, sometimes it's harder to see. I'm going to go over here to these whole numbers so I can kind of get an idea. If I wanted to go from 2 to 10 and I'm thinking about first differences, I would have to add 8. Well, 0.4 plus 8 is not 2. So what I'm going to do is I'm going to see what that difference is. So I know this isn't linear because my first differences are not the same. So I'm going to take a look. I'm just going to say 2 minus 0.4 so I can find out what their difference is. This is plus 1.6. And then I'm going to do the same here. 0.4 minus 0.08. And we got 0.32. Okay, so my first differences aren't the same, not linear. So I'm going to check my second differences. I got 1.6 minus 0.32 gives me 1.28. And I can see this is not going to be the same here. I'll just verify it. 8 minus 1.6 is, I'd have to add 6.4 there. So my second differences are not the same. So it cannot be linear, it cannot be quadratic. So now I got to look at exponential, where we see the y changes more quickly than the x's. You never see the same y value twice. And there's a common ratio, meaning a common multiplication pattern. So let's take a look. Our x values are changing by 1, but notice the y values go from 0.08 to 0.4 to 2 to 10. They're growing much faster. So really we want to see if there's a common multiplication pattern. So we're not going to look at any of this anymore. That's not going to help us. Decimals, sometimes we don't like looking at the decimals, so I'm just going to look here. If I say 2 times 5, well, that's definitely 10. So I'm going to try it again here. Is 0.4 times 5 2? Well, let's take a look. 0.4 times 5 is 2, okay? And then is 0.08 times 5 0.4. 0.08 times 5 is 0.4. I found a common multiplication pattern, multiplying by 5. This is exponential. Okay, sometimes our tables are turned the other way. These say the same thing. It's just whether you presented them vertically or horizontally. We're still going to look at the y values for our differences. So when I look from here to here, -5 to -4 is actually +1 because you're going less negative. -4 to -1 is +3. So now we know this is not linear because the first differences are not the same. -1 to 4 is +5, and 4 to 11 is +7. So the first differences aren't the same. Let's look at the second differences. 1 to 3 is +2. 3 to 5 is +2, and 5 to 7 is +2. Our second differences are the same, making this quadratic. All right, 2 more examples. Okay, take a look at number 13 here. To go from 5 to 9 is +4. 9 to 13, +4. I'm starting to think this might be linear because we have the same number going here. Let's keep verifying. 13 to 17 is +4, and 17 to 21 is +4. So this would represent a not a quadratic, a linear. If it's the same number each time in the first differences, it is linear. All right, let's check our last one. 0 to -1 is -1. -1 to 0 is +1. 0 to 3 is +3. And 3 to 5 is +5. So not linear. Check here. -1 to 1 is +2. 1 to 3 is +2. And 3 to 5 is +2. This one is quadratic. All right. Hopefully that was helpful. Check your first and second differences. Look for common multiplication patterns for tables. The equations, you're looking at the exponents. Let me know if you have any questions. See you in class.